Good morning, everyone. Welcome, Jianfei. And he's very young. He's a very talented scientist. He comes from Nanyang Technological University, and he has won a lot of prizes. For example, I'll show you. uh, okay. He was recognized as the top award top 2% scientist combined by Stanford University and the Forbes Asian 30 under 30 list. So he's very talented. So welcome him. He will give a talk about building world model intelligence, the crucial role of perception. Welcome.
Okay, good morning, everyone. I'm very happy and honored to give this talk in ICBS 2024. Yeah, I took a long flight from US to Beijing. So today's talk is about actually perception. But perception is a very important topic in building a strong AI systems, and we call it world model intelligence. So we have known that the large language model has been very useful. I know in abroad we use ChatGPT, Claude, and Google Gemini. In China we have the Kimi, right? I think maybe many of you have been used this before. So it shows amazing capabilities of dealing with some text and image tasks, such as you want to write something or you want to generate some images, you can use these models. But it is enabled by three things. The first one is the deep neural networks, and then is a massive training data. You know, all of the deep models are actually trained by thousands of data. Actually cost around maybe $2 billion for OpenAI to build the ChatGPT. And also thousands of GPUs, which are also very expensive. So we can see that for large language model, we can just give some instruction like write an invitation letter to the participants of ICBS 2024, or you just like design a simple logo for the ICBS. Then you can get the image you want and the letter you want within 1 second. So this can improve the efficiency of our work. But how does the current AI understand the world? So we see how we build these large language models. So the physical world is like this. Then we describe this physical world by text and images. Why do we use these kind of data? Because these data are very easy to obtain. In Google or in Baidu, you can get free text and images. And thousands of these data can be obtained for the model training. And then we use these two data modalities to describe the physical world, and then we build the large models to learn the text and images. So basically, the physical world is modeled by the text and image embedding space. But we think about this is not very reasonable because in our brain, in our human brain, we never describe something in our brain using language. We actually have some other thinkings and logics to describe the physical world. So LeCun, this is the Turing Award in 2022. He proposed a new paper called World Model. So he said that actually the large language model can only be a part of the intelligence. We call it intelligence. So there should be other things. For example, when we put the large language model here in the world model, there should be other components like the short memory, because we need to have some short memory like what we learned today. And also the perception. Now we use eyes and we use other sensory organs to perceive the world. And we also have a configurator. For example, we should have multiple modes of living and thinking. For example, now you are listening to my talk. So your configurator should let your brain memorize more knowledge. And sometimes when you are playing computer games or playing smartphone games, then your configurator maybe just to let you have fun and never memorize anything, right? So there should be a configurator. But now most of the models only run in one mode. That is to answer your question. Okay, so it is not real intelligence. And different kinds of modes should have different cost. For example, yeah, when you are listening to my talk, you may feel tired after 1 hour, but when you're playing games, maybe 2 hours, you're very happy, right? So they have different costs. And then according to the perception of the world, you need to have different actions. So in the world model, all of these components should be considered. But now we only consider the world model here, the green part. So this is the language models. That is to mean we embed all of the information in the physical world into the semantic language space. We use language and image to describe everything. Okay, so perception and action should also matters in building a strong AI model. So from the vision language model here to the real artificial general intelligence, we think that two other things should be unconsidered. The first one is the perception. The second one is the interaction. Yeah, according to the world model. So the interaction is actually the robot we call the embodied AI. We can build some models to control the robotic arm or control the drone to do something. This is the interaction. But what about the perception? So today's talk is more about like a brief introduction of recent progress in my group for the perception. So currently, we already have many AI-enabled perception systems. For example, yeah, in this room we have the what is called the video surveillance to monitor everyone. This is mostly for the security application. And also in the Apple Vision Pro or some AR VR gaming, the camera can capture your motion so that you can play some games, right? And sometimes some of you may wear the smart watches so that they have the data for your heartbeat, for your vital sign, so that they can monitor your sleep. So these are some existing AI-enabled perceptions. So today's questions including several parts. So the first one is what are the current perception solutions? The second one is, can we provide more perceptions for a better AI construction? The third one is, how can we enhance the large language model with perception so that we can build the final world model? So we start from the animals or the human. How do we perceive the world? So actually, biological studies show that more than 70%, so around 80% of the information are obtained by our eyes, which are the visual information. So the sunlight goes to the objects, and the reflected light can be absorbed, yeah, and captured by our eyes. And these information can be mapped to our brain to build the 3D world. So we can see that this is the visible light of the spectrum. So similar to this, human just make the cameras according to our eyes. Okay, so for example, when we want to capture this image, we actually map these continuous light spectrum to the discrete matrix like this. Okay, so this is the RGB photo. So there are 3 channels. So basically, compared to our eyes, the cameras are not very good because it only captures 3 channels, the RGB channels. These are 3 points on the spectrum here. However, our eyes can capture many spectrum, the whole spectrum of the visible light. So it has many applications in our real world. For example, we'll drive the car, the traffic violation detection enabled by the cameras. Okay, so I think, this is the most common application in our daily life. So we think about, is there any limitation for the visual perception? So there are 3 major limitations to use cameras in our daily life. So the first one is the privacy issue. You never want to install a camera in your bathroom or in your bedroom, right? Because it arouses some privacy issue. And the second one is in autonomous driving or in the drone vision, when your camera is moving fast or the object is moving fast, this motion blur can happen. Okay, so these can prevent the AI to have a good recognition results. And the third one is the dark environment, the low illumination issue. So in at night, actually the computer vision cannot be well applied. But dangerous things like fighting or some bullying commonly happen in this kind of environment, right? Yeah. So we see that the current perception is mostly enabled by the visible light. That is the camera. Okay. But actually, in the electromagnetic spectrum, there are many kinds of waves that can be used for perception. For example, this radio frequency signal. So in our daily life, we can see many kind. We actually are surrounded by many kinds of radio frequency signal. For example, when you pick up a phone, actually a RF signal is sent from your phone to the base station, carrying your voice, and then it will come back. Okay, so actually the radio frequency waves are everywhere in our human society. So when you go back to your home, the first thing is actually to connect to the Wi-Fi. Whether you are conscious of this, your phone will automatically connect the Wi-Fi. So we are wondering if we can use this kind of radio frequency signal, the wireless signal, to do the perception for AI. Yeah, so Wi-Fi has been very ubiquitous infrastructure for internet connection. Whether you are in the smart home or you are in the office, you always have this Wi-Fi signals. So if we can see the Wi-Fi signal in your home, for example, here. So this is a layout of a home. Okay, so this is a living room, and you put a Wi-Fi access points here. The red region shows the stronger signal of Wi-Fi. Okay, so I guess you always want to stay in the red region so that you have the very strong Wi-Fi access points. And the Wi-Fi signal cannot cannot go across these walls in a very good manner. So we can see that the Wi-Fi signal can detect your phones. Okay, so whether you are conscious of this, your devices that are connected to the Wi-Fi access points can be perceived by your Wi-Fi by the wireless signals. So we have another question. What if the Wi-Fi can sense humans? Is it possible? So actually it is possible, because when the signal goes from the Wi-Fi access points to your laptops or your cell phones, the signals actually propagates around this space. Okay, so it have a multi-path effect. Some of the signal just go through our body, and some of the signals actually are reflected by the walls. But finally, all of these signals will be sent to your phones so that you can use the internet. So we can see that if we capture these wireless signals, we can see that this signal can be used to indicate the patterns. Okay, so when I walk into this room and then I take a seat, then some patterns can be captured. So using deep learning or machine learning, we can analyze these patterns to get the human. Okay. So the Wi-Fi sensing data includes two types. The first one is the signal strength. So before 2011, we have the received signal strength. So this one is very simple, because in your phone, that symbol indicates the signal strength. So how strong the Wi-Fi signal is in your phone means how strong, how fast you connect to the internet. And after 2011, people start to decompose this data to the channel state information. So this is a kind of communication data. If you major in communication, then you should be very familiar with this one. So this CSI data, we call it, so it's a complex value matrix that describes the wireless signal propagation from the transmitter to the receiver. Okay, so it is a very big matrix. So it's very similar to the RGB images. The RGB images is actually 3 points, red, green, and blue in the visible light spectrum. But this one is that, oh, sorry, okay. For the CSI data, how many antennas you have, then how large the resolution of CSI data you can get. So with the CSI data, we can see we can get very high resolutional perception data for human perception. So this is a pipeline for the perception. It's quite simple. When a person goes between the Wi-Fi access points and like smart appliances or your phones, then we can capture the CSI data, and then we can develop some signal processing and deep learning models to analyze the human activities. Yeah, so here is the data we captured in our real experiments. So we can observe that the CSI data is very smooth when there's no one in the room. Means that when this room, there's nobody here, the Wi-Fi signal are very robust, okay? And it shows like this. But if someone comes into the room, the wireless signals in this room vary a lot. There are many fluctuations caused by human movements, like you walk around here, or I just swipe my hand. All of these human movements can cause the fluctuation and variations of the wireless signals. Yeah, so according to these patterns, we can actually use some statistics to describe this process so that we can get this one. So when someone is occupied, this statistics called signal tendency index can indicate whether there's a person here. Yeah. So there's some kind of demo here. So based on the Wi-Fi, we actually deploy 2 pairs of Wi-Fi in 2 meeting rooms. So the first meeting room, we put the Wi-Fi here. Okay. So here's a Wi-Fi router. So when a person goes to a conference room, then we can show that the wireless, only by Wi-Fi signals, we can get the movements of this person, indicating the room has been occupied. And then when the person goes out, it will also be indicated. And then the person went to the this small conference room. So this is another Wi-Fi access points. Yeah, so indicating that this small room has been occupied. Okay, so this is a simple demo in our university. So we know that we can model in the wireless signals using simple like signal processing or machine learning. So we also have another question. Can we describe this kind of RF signal by simply some mathematical modeling? For example, like 100 years ago, there are some theories called Fresnel zone to describe the optics and radio. Okay, so it shows that when you send a signal from a transmitter to a receiver, just the transmitter is like your Wi-Fi access points. The receiver is basically your cell phone or your laptop. Then it can be described by ellipsoid. Okay, so the 2 TX and RX are the focal points of the ellipse. So this theory can be used for many like radar systems and many kind of optic systems. However, in Wi-Fi or communication signal, this does not really apply. So no, in physical manner, it applies. But in our real life, this is too complicated to analyze using this kind of theory because our layouts are changing all the time. If you change the environment to another complex environment, this kind of theories is too simple to describe this kind of situation. And also, you can always move the position of your access points of your Wi-Fi routers, right? And all of these actions can cause the ineffectiveness of this theory. So it has some limitations. When we only want to achieve some simple application, simple activity recognition, we can build some models, rely on this theory. However, if we want to recognize some very complicated actions, this theory cannot describe this well. So we need to rely on the machine learning and deep learning. Okay, so this is the significance of why we use deep learning. We want to get some fine-grained patterns, some complicated patterns by deep learning. Yeah. So now we have already detected whether a person is in this room. So the next step is to analyze what we are doing in this room. Okay, so we want to recognize the activity. So we can see that this is the raw data of the channel state information. So when the room is empty, it's quite stable. So when a person goes to this room, the Wi-Fi signal is actually varying a lot. And then when you are running, the variation of the signal becoming larger and larger. When you are like lying down or standing up, there are also some variations. So we see that the statistical patterns can indicate the spatial information of the wireless signals. And the time series features can indicate the motion, like you are standing up or you are lying down. These are some motions. They can be described by the temporal features. So we can use some simple statistical learning methodology to recognize these things. For example, we can just model the dynamic activities by like PCA plus some SVM or random forest. This is enough. Okay. And for some static posture identification, we can also use some like the Pearson coefficient, so that we can measure the similarity between different postures. Okay, so we can use some simple statistical learning to recognize the human activities. So we also have some demo in our lab. So here we see that this is Wi-Fi access points deployed in this room. Yeah, so this is like 8 years ago what I was like, a little fatter when I was in PhD. And yeah, so we put 2 routers in this room. The distance between the 2 routers are around 3 meters. And all of the algorithms are actually conducted in this laptop. So we can see that it can recognize my moving patterns only using wireless signals. Okay, so this is quite helpful for some like elderly care or for some other applications, because we can't install the camera in your bedroom or in your bathroom, but we can use the Wi-Fi signal and the radio frequency signal to detect some dangerous actions, like you're falling down or the stop of your vital sign. Okay. So now we have already recognized the human activities. So next step is to recognize some subtle movements like the gestures. Okay, if we can recognize some gestures, we can use this gesture to control like some robots or to do the human-robot collaboration. So we also show the data here. We can see that when you do different gestures like the pushing and pulling, the signal shows that there are some unique patterns that can be captured. Okay, so these kind of patterns are too subtle to be captured by traditional machine learning models. So we still need to use the deep learning techniques to capture these patterns. But there are some challenges in the gesture recognition. For example, the movements are very subtle. The environmental dynamics, the environment noises are actually larger. And we do not have many data to train this model. So it's a few shot learning. We need to leverage limited training data. So to overcome this question, we propose a few shot learning network based on the contrastive learning in 2018, actually. So at that time, contrastive learning was not so popular as the current time. Okay, so the basic idea is that we collected some data for each gesture, and then we use a deep neural network to get their embeddings. And then every time when you test this model, you only compare the data to the template data you have collected. So this is the basic idea of the few-shot learning and the prototypical neural network. And how is it trained? So the contrastive learning means that we want to minimize the distance between the template data and the test data. So by training this model using the contrastive laws, we can get a few-shot learning network using only around 10 samples per class. Okay, so the final results show that we can achieve very good results only based on 10 samples per gesture. Yeah, so we also build the same demo in this environment. So you can see that we put a pair of Wi-Fi access points here, and then we connect our system to this laptop. And the laptop is playing YouTube videos. Sorry. Yeah, so when I perform some gestures, then these gestures are captured by the wireless signals, and the wireless signals are analyzed by the deep neural network, and then the deep neural network controls the YouTube channels to switch the channel. Okay, so you may think that this is too like in a prototypical way, because no one will put your Wi-Fi access points like this, but this is like the initial stage of the research. To do research, we never assume like we can achieve a very cool demo in one day. Actually, we need to do it step by step. So this is a initial stage to show that this is possible, and then we can generalize the environment, generalize the model. Okay, so the research is done by step. Yeah. Yeah, sure. Yeah. No camera is used. Yeah, so it's simply achieved by analyzing the radio frequency signal around the air. Okay, so they are captured by by these two Wi-Fi access points. Yeah, and then we also do some very interesting work to show that the Wi-Fi and the wireless signals can even tell who you are, because we know that when we walk, the gait are actually unique patterns. When your gait is changing, then it shows some maybe some health condition, okay, some health issues when your gait is changing. And also by analyzing the gait, we can identify different persons. Okay, so we show that when a person is walking in this room, okay, you just simply walk. We can use the radio frequency signal to analyze the gait patterns. Okay, so how you walk. So everyone walk in a different way because the speed of your hand, the speed of your leg are all different. Okay, so the gait patterns are different. So we can also use the wireless signal to get this means 5 different persons. Okay, each color indicate a person. So we can see this is one step. Okay, so this is like in your WeChat step counting. So this is one step. Okay, so we can see different person has different patterns of the step. However, for the same person, their patterns are quite unique. So according to this observation, we can use the Wi-Fi signals plus some deep learning ways to recognize the gait. And furthermore, we can even achieve higher resolution. For example, the human pose estimation. So the current solutions are still realized by the cameras. So using camera, I think maybe many of you have used the camera to play some games, and like the tennis game, right? So when you're playing tennis game using the Xbox, you actually the camera capture your pose. So this is called pose estimation. So the pose estimation transforms the image data of a human being to the pose. We call it pose landmark. Okay, so everyone's skeleton can be described by 17 key points. Okay, so it's like your head and your hand. So we also try to build a model only using the radio frequency signal to capture the human pose estimation. However, we don't have so many data to train the model. So the basic idea is to use a computer vision model well established by the current companies like Microsoft, Xbox, Kinect. So they already built a very good model using the cameras. So we use this model to teach our Wi-Fi models. So this is called model distillation. We use one teacher model trained by one kind of modality. So this modality has been well trained, and there are so much data in the computer vision field. However, in wireless signal field, we don't have so much data. So we can use one teacher model to teach another student model, so that finally our student model can recognize the human pose only by the radio signals. Okay, so this is the idea. And we can see some results in our lab. Yeah, so the left the left one shows the vision results. So this is so these poses are actually estimated by the cameras and computer vision models, and the right one are analyzed by only the radio frequency signals. It's the Wi-Fi signals. Okay, so we can see that it's not so stable, and the yellow region shows the error, shows the errors. However, it's being good enough for many applications, like doing some AR and VR game, or you want to monitor the health and activity of the elderly. Okay, and it does not arouse any privacy concern. Yeah, so this is a recent work published in 2022. Okay, so there are still some challenges of AI-enabled radio frequency sensing. For example, the data hungry, domain-specific, and security. I will introduce them one by one. So the first issue is actually the radio, the radio frequency. Yeah, the first issue is actually the data issue. Because existing deep models, as we said, they require massive label data. But for computer vision models and language models, we always have this data because this data can be obtained from the Google and Baidu in a free manner, right? It's free launch. However, in our field, it's very hard. If you want to recognize a falling activity, we need to collect the data for the falling, right? So we need to ask our PhD students to do the falling in our lab for hundreds of times so that we can capture this kind of activity, right? But yes, this costs students. This does not cost, yeah, right? The students are not happy, right? So if you want to recognize the falling activities, we cannot rely on the students to collect the falling activities day by day, okay? So we need other techniques. So we can propose some neural networks using self-supervised learning. So the idea is that we just put the Wi-Fi routers in this room, okay? And then we collect the data day by day. All of the data are random data, like you are walking here and there. I'm giving the talk and you are listening to the talk. All these activities can be captured by the radio frequency data. And then the self-supervised learning is a kind of neural network and objective function to capture the movements inside this data using a contrastive manner. That is to say, for example, here is a loss function. So we augment one sample, like you are sitting there. So we can augment it to several versions. Yeah, you can sit in here and you can sit in there. And these are the same patterns, okay, because you are always sitting. But this activity pattern is different from the walking patterns, okay? So by distinguish different kinds of activities, simple activities, we can use the self-supervised learning to train a model in advance, okay? And then the student only need to collect the following patterns for several times, like 5 times or 6 times, then a well-trained neural network can recognize it. So the basic idea of the self-supervised learning is that by self-supervised, by training the neural network using the contrastive laws, we can get a very good feature extractor by massive unlabeled data. And afterwards, we fine-tune this model using labeled data, but only few samples. Okay, only 3 to 10 samples, we can get a very good results. So this is the idea of the self-supervised learning. And the second one is the domain dependency. The domain dependency means that we train a model in this room, but we want to use this model in another room. We find that the generalization ability is very bad. The reason is that the layout of this room is different from a new environment. So how the wireless signal propagates from the Wi-Fi access points to this laptop become different. So you only model the situation in this room, but you do not model this situation in all of the rooms. So they cannot be generalized. This is a common issue also in the computer vision field, because when we want to recognize something, the background of the image is always changing. So this is called domain discrepancy. Okay, the domain discrepancy is a very severe issue. It's actually the distribution shift between among environments. Okay, so we can use domain adaptation, domain generalization models to overcome this issue. So the basic idea is to extract the features, the common features across these environments, across these different environments, and to discard, forecast the information across the environments. That is to say, we only extract the human motion in different environments, and we discard all of the other environmental information so that the models can only recognize the human motion. So this is how we use the domain generalization models to overcome the distribution shift. Yeah, the distribution shift is very common in computer vision, in natural language processing. Yeah, so this is the basic idea. We have 3 environments, we train 3 models, but actually you can see that when we want to use this classifier in another environment, they do not apply, right? But then we minimize the distribution distance between these 3 environments. Then we get a new classifier in a joint distribution. Okay, so this is the main idea. So this can be achieved by minimizing the distribution distance, like the maximum mean discrepancy or the wall system distance in the feature space of deep learning, of deep neural networks. So the third issue is to enhance the security. We can see that in image, when we add some Gaussian noise or white noise to an image, the original deep neural network cannot recognize it anymore. So this also applies to other data modalities, like in the radio frequency. So assume that you are lying on the bed, okay? However, suddenly the neural network recognizes that you have a falling dangerous activity. So how does it happen? Some hacker just attack your device and add some noise to the data, and then your model cannot recognize it anymore. So this is called adversarial attack of the deep neural network. So it's not very safe. So this is so the security issue is always a big issue. So we can use some like simulation or some data augmentation way to increase the robustness of the neural network, or we can detect this kind of attack in advance so that the hackers cannot attack your devices. Yeah, so finally we developed this wireless sensing systems. Okay, so now it has been US patents, PCT patents, and it has many features. And we released the first Python library for the radio frequency sensing 2 years ago. So in the past 8 years, my work actually goes from sensing platform. Then we developed the tool and the library based on the system, and we enable many sensing tasks like the pose estimation, activity recognition, gesture recognition based on the platform and deep neural networks. And then we study how to improve the extensibility, security, efficiency, and robustness of the radio frequency sensing. Okay, so this is the overview, and each block indicates one paper in the past 8 years. So there are some new trends on sensing and perception. So I would like to talk about 3 parts. The first one is a new standardization. The second one is multimodal learning. The third one is how to integrate these kind of radio frequency sensing with the large language models. So the first part is the Wi-Fi standardization. You may ask me a question that when can we use your technology in the future? Okay, so this is a very good question. So IEEE has already working on this. They will release a new Wi-Fi standardization called 802.11bf. So this edition will come into existence in 2025. So in 2025, most of the Wi-Fi infrastructures can have the ability to sense the person. Okay, so we can extract the sensing data from the Wi-Fi infrastructure. Okay, so this is the standardization. So when a new standardization comes into existence, most of the Wi-Fi router company will use this standardization, like Huawei, like Cisco, they will start to use this. So at that time, all of our previous research works can be applied to the existing Wi-Fi infrastructure so that you can use our AI functions in our daily life. Okay, so this is Wi-Fi standardization. So in this standardization, we can see that they also add the 60 gigahertz. Okay, the 60 gigahertz. So the 60 gigahertz means that higher frequency of the signal have been added to the Wi-Fi signals. So the result is that we can have better and better sensing data because the higher frequency you have, the better resolution you have. Okay, so if you have a very high frequency, higher than the visible light, then actually it's X-ray. Okay, the signal can go through your body, and you can even get the X-ray. So in the standardization, they increase the frequency so that we can get better results. So we also use some 60 gigahertz radar. So currently they are not combined and integrated into the Wi-Fi infrastructures. Now they are only provided by some specific devices like this. Okay, we call it 60 gigahertz radar. So we use this radar to do some imaging. We can see that only by the 60 gigahertz radar we can get the human body, and we can develop some some models like the diffusion models to recognize the human pose in a very clear manner. So I will not introduce the details of the models. So basically, the diffusion model, the objective is to denoise the data and transform it to another distribution. Okay, so it is widely used in the image generation and video generation. You may see some news like the Sora, the video generation model by OpenAI. So that Sora model is also developed by diffusion plus some like VAE. Okay, so the diffusion model basically denoise the data and then transform it to another to another data modality, to another distribution. Okay, so we use this diffusion model. We can find that from this kind of very noisy data. Okay, the red points is the data. We can restore the human bodies using the diffusion models. So this work is a very new work in this ECCV 2024, and we will present this work in Italy this year. Yeah, I will skip this one. And using the 60 gigahertz, we can see that the pose estimation results are better. Okay, so the left one is the raw data. It's the sparse point cloud captured by the radio frequency signal. And then the medium one is some current models. And the last one is estimated by the diffusion models. We can see that it's very robust, right? It's not shaking anymore. And only by very few points, a sparse matrix, we can estimate the person motion and pose in a very accurate manner. So in the future, apart from Wi-Fi communication, in the 6G communication, they also add some signals for sensing. Okay, so now you are using 5G. You think that there might not be a big difference between the 4G and 5G from the experience feeling, because we do not see many improving bandwidth for the communication. But in the 6G, they integrate the sensing part into the communication, so that in the future, when you use the 6G, you can be detected by the 6G, by the signal, and you may be even localized by the 6G signal. Okay, so this is the same principle behind these technologies. Yeah, so the final perception should be performed by multi-sensor solution. Like we have cameras, we have wearable device, we have mmWave radar, Wi-Fi, 6G, and so many kinds of radio frequencies and cameras. We can integrate all of this data to get a complete description of this world, of the physical world. Okay, so we also released a new data set. We use 5 modalities to capture the human motions, and these are the 5 modalities, including the RGB, the depth image, the Wi-Fi signals, the LiDAR, and MM-wave radar. Okay, so we integrate all of these sensors to a robot, and then we move this robot to capture many data in our campus. Yeah, and there are already like more than 50 teams using our data sets to build some new perception tools. Yep, because they can combine like 2 of the modalities for better sensing results. So this work has been published in the New Rips last year. So my final topic is how to integrate the multimodal sensing with large language models. So we think that by better perception, the perception is very important because it bridges the gap between the large language model and the physical world. Now the large language model can only think in the semantic space. They model every concept and objects only using language and feature embedding. This is not right. So by perception, we can bridge this gap. We can connect the language model to the physical world. So we can input all of these data into the large language model and use these data to train a new model that is able to perceive the world. Okay, so previous AI can only predict what it learns. For example, if you only train this AI with running patterns, then it can only recognize running. But now, using the large models and more data, we can map the sensor data to the language space. So when the AI learns standing and walking, okay, now we have the data for the standing and walking. Then the AI can guess running, because from the semantic space, we know that running is to walking faster, okay, and standing is to keeping still. So in the semantic space, we know that these words have some connections, and there are some correlations between these words. So when we map the IoT sensor data or the vision data into the language space, we can also have similar effects, so that we know, like, we can let the AI to guess some new concept based on what they have learned before. I will skip the details of the paper. So basically, we just align different data modalities to the language feature space. And so we can apply this technique to many modalities. For example, the Wi-Fi we mentioned before, the MM-wave radar, and some other IoT sensors. So if we can connect all of these sensors to the large language models, the models can be more useful for our human society. For example, in our like industrial applications, when we connect all of these smart sensors to the large language models, they can help the people to like monitor the smart manufacturing. For example, you can simply ask the models, tell me the sensor data of the machine at a specific time, and then it will go back to the database and get this IoT data. And then you can let the large language model and our IoT model to analyze stop the machine when the temperature goes above 60 degrees at midnight. And then the large language model can generate the codes according to the rule and embed this code to the smart machines. So finally, we can reduce the human effort in the smart manufacturing. Okay, so there are many applications like this. So this is one example. Yeah, so here's the summary of today's talk. So firstly, to build a strong AI, we need the AI to perceive the world, not only think in the semantic space. And to perceive the world, more perception methods are required. For example, the radio frequency and even other acoustic or IoT sensors. And the radio frequency sensing can provide very good results. And the future Wi-Fi and 6 gigahertz, 6G, 6th generation communication can make this kind of sensing ubiquitous, because these radio signals are everywhere around the air. And when we integrate all of these sensing techniques with large language models, we can enable the AI to really interact with the world, not only understand the world. Okay, so this is my talk today. And yeah, this QR code is my homepage. Yeah, if you are interested, you can scan it and visit my homepage. Thank you very much.
It's a very interesting talk. Do you have any questions?
I have a detailed, thanks for impressive talk. I have a question about is some electric equipment like a cell phone will severely affect your result when you use Wi-Fi to detect the gesture like stand or move, because they also provoking Wi-Fi signals.
You mean the
yeah. Your watch or your cell phone will make noise that makes the Wi-Fi cannot
unstable, right?
Yeah.
Yeah. So currently, we only consider the transmission between the environmental Wi-Fi. For example, in this room, we actually have two Wi-Fis. So one is here, other one is there. Okay. So they are transmitting data. So we can use the signal propagation between these two devices. So in the future, we may consider to use like the Wi-Fi access points between the Wi-Fi routers and your phones, right? But when you are moving your phones or moving your smart watches, there are many noises.
Yeah. So I mean, in your video, did the person did he carry cell phone, or they just have no electric equipment?
Oh, you mean during the experiments, right? Yeah, they can carry their own phones here.
Oh, so it will affect so much when you carry.
It will not affect a lot. However, if you bring like an iron things, a big one, to put it just under the Wi-Fi access points, then it will block all of the signal, right? But only a phone, it does not matter much. Yeah, we see that maybe the electronic monitor, I mean the monitoring or the laptops may affect more if you carry it. Yeah.
I see. Thank you.
Thank you.
Any other question?
Are the health issues well understood concerning going to higher frequencies in Wi-Fi?
Oh yeah, I mean, if we increase the frequency of the Wi-Fi signals, right?
Well, how does it interact with the human body? I mean, can it be harmful, right?
Yeah, this is a very good question. Yeah, so you see this news. So that's why we need some standardization organization to make the standard. Yeah, because we only study how the radio frequency can sense the human body, but we do not consider how bad it is for our human body, right? Maybe the current Wi-Fi can already be harmful for our human body, but this is what the IEEE need to consider it when they do the standardization. They need to do many experiments and how they can be harmful for the human body. But previously, I've read many papers in this field. It's most of I think it's affected by the power of the signal. So the current Wi-Fi, the power is very low, so it does not affect. However, in some scenarios, like in the industrial manufacturing, they use very strong Wi-Fi signals to cover a large area of the factory using only one device. Then the power of that Wi-Fi access points has already has already exceeded the IEEE standardization, and then it can be harmful for the person. Yeah.
So when the body moves very fast.
Yeah. Yes.
So what is the standard speed that you can capture?
You mean the speed?
Body movement.
The body movement. Yeah, this is this is a good question because it's very hard to get a specific walking speed or running speed because the Wi-Fi signal is captured by off-the-shelf, the commodity Wi-Fi. So it is not, the signal is not tailored for perception. So we can only capture the patterns and analyze, okay, this pattern is walking, this pattern is running. However, we don't have we cannot calculate the specific number for the walking speed because we cannot use the Fresnel zone theory to analyze it. The major reason is that the environment is too complicated. We cannot only use the signal theory to analyze the signals. There are many signals in this room. Yeah.
So if the ball is farther away, then you would have also difficulty?
Further away, you mean?
Well, instead 10 meters, maybe 20 meters away.
Yes. When the signal is very weak. So the sensing range is specific. Like between the transmitter and the receiver, there are ellipse. But beyond this ellipse, around maybe 3 meters away, then the signal cannot detect your fine-grained activities. But only some like dynamics when you are walking around, then they know there's a person there, but they cannot detect what activities you are performing. Yeah.
Did the distance that between the Wi-Fi and the whole human body will affect the mode of the your results, such as when I lived 3 or 4 meters away, or I just stand by the Wi-Fi? Did the mode that you detect will be different?
Yeah, because there's a specific sensing range.
Yeah.
So beyond this range, they cannot detect you anymore.
Yeah, I know. But in the range, when you close and when you just far away, I think they may be slightly different.
You mean there's some different, but in our results we show that they can all be detected. Yeah.
Okay. Thank you.
So this is not a very big issue. Yeah, but if there are many people standing in the line of sight of the signal propagation, then it has some difference. Like a group of people just standing here blocking the signals, then the perception can be affected. Yeah.
Any questions? Okay, I have 2 questions.
Okay, sure.
The first one is, how big are these models do you use? For example, how many parameters?
You mean the deep learning models, right?
Yes.
Yeah. So it's quite small. It's I cannot tell like the exact number of the parameter size, but it's just like 5 convolutional neural networks, like the LeNet.
Okay, it's very small.
Yeah, because we also have a research paper discussing it, that under what circumstances should we use larger model or the smaller model? Because currently we can see many papers, they just apply very large models in many fields. But this causes overfitting actually. So the generalization ability is very bad. So in the statistical learning, there's a theory telling us the simpler model you use, the better generalization ability you get. So in some circumstances, we should choose the smaller model if the loss value can be the same between different sizes of the models. Okay, so here we choose the smaller model because it has better generalization ability.
Okay, Thank you. And another question is a very general question. So I know you do some large language model. So do you have any suggestion for researcher in university? Because in university, we always don't have too many computing source. So do you have any suggestion?
Yes. I think this is also a very good question. Because when last year December, when Jensen Huang, the CEO of NVIDIA, come to Singapore, we have a talk, and I asked him this question. I say, our university has only maybe 100 GPUs, and this is what we have. But in Google, in Alibaba, they have thousands of GPUs. So these researchers can publish good papers on large models easily. How to deal with it? So Jensen told me that, do you have a sports center in your university? I say, yes, we have. And he asked me, did you have a good library in your university? I say, yes, we have. Then he said, why not the university or the city can build some GPU or data center in your university? especially for the researchers and students. Okay, so this is this is like a salesman because he want to sell his GPUs more, right? But from our university side, even though we only have like 8 GPU, 4 GPUs, we can still do good research because good research does not always mean better accuracy or better performance. We need to study the fundamental things using less GPUs. For example, my first paper in CVPR 2017 only costs 1 GPU 1080, and it's an oral paper. Yeah, the top 2% paper. We study how the convolution layers perform linearly, and how can we how can we modify the convolutional layers to make it perform non-linearly? So simply use some kernel methodology. So this does not cost a lot of GPU, but it's worth a try in the university. We need to study the fundamental things, the fundamental theories, and see how is it performed. So for example, the ChatGPT is very good, shows very good results, but I think it's still a black box in its 90% of the model characteristics. Okay, so we can actually study like the fairness, like which parts of the model parameters can correspond to which part of the features or the real world, and how the model think for some specific questions. And there are many, I think there are many research questions can be studied using very less GPU resources. Yeah.
Okay, thank you.
Yeah,
Thank you
and they are very valuable. Yeah.
Yes.
Oh, okay, thank you. I'm an assistant professor in Nanyang Technological University in Singapore. Yeah, but now I was a visiting researcher in Harvard. Yeah.
Okay, any questions? No, thank you. Thanks again.